In this video, we're going to talk about rational functions. Now, a function f is said to be a rational function if it can be written in the form p of x over q of x, where p and q are polynomials. So any function that can be written in the form of a polynomial divided by another polynomial, that's a rational function. So let's look at a few examples. The first one here, f of x, is clearly a rational function. We have a degree 3 polynomial up here and a 6th degree polynomial down in the denominator. Right? So it's a rational function over a rational function. Now the next one, I've called it g instead of f, and I've used a different variable, t, instead of x, but this also is a rational function. Now you might think, 1, is that really a polynomial? Well, yeah, a constant function will be a polynomial. In fact, a constant function is like a degree 0 polynomial. And then t minus 3, that's a linear function, that's a degree 1 polynomial. Okay, and then same thing here with r of x. Now I've written it in factored form, but you can see that if you multiplied everything out, you'd have a polynomial divided by a polynomial. So that's a rational function. And now the last one, k of x, it might not look like this is a rational function. It's just a polynomial here, but we could think of this as being this over 1. Okay, and 1 is a polynomial, and so this is a rational function. So any polynomial could be thought of as a rational function because you could think of it as that polynomial over the polynomial 1. Okay, now how can we find the domain of a rational function? So the domain is the set of all possible inputs for your function. So what are they going to be the inputs that we can't put into a function? Well, those are going to be the inputs that make the denominator 0. Okay, so when you're trying to find the domain of a rational function, you're just going to exclude the numbers that make the denominator 0. So what you'll need to do is factor the denominator. Okay, so we can write this as 3x minus 4 over, okay, and if we factor things down in the denominator, we can factor it as, let's see, x minus 5 and x plus 2. Is that right? So notice we have a minus 5x and a plus 2x, that's minus 3x, and minus 5 times plus 2 is minus 10. So notice x cannot be 5 and x cannot be negative 2. So it's the set of all real numbers other than 5 and negative 2. So how would we write that in interval notation? Now if you think on a number line, negative 2 is over here and 5 is over here. And so we're going to include all numbers on our number line except those two numbers. So we're including the interval between the two numbers, the interval to the right of them, to the right of 5, and to the interval to the left of negative 2. So notice it'd be the interval from minus infinity to minus 2, and we're not going to include 2, so we put an open parenthesis there. And then the interval from minus 2 to 5, and then union with the interval from 5 to infinity. Okay, so that's the domain in interval notation. And in case you're wondering, here's what the actual function looks like. Here's 3x minus 4 over x squared minus 3x minus 10. Notice that our domain excluded the number negative 2, and at negative 2 here we have a vertical asymptote. Okay, and same thing at 5. Our domain excluded 5, and so we have a vertical asymptote there. We can kind of zoom in and get a little bit of better picture of the graph. Okay, and that's what the rational function looks like. We'll talk about vertical and horizontal asymptotes in a later video. Okay, let's do another example. Let's move down here. Find the domain of the function f of x equals x minus 2 over 2x cubed minus 13x squared plus 18x. Write your final answer in interval notation. Okay, again, we're going to have to factor the denominator. Okay, so when we factor things, we notice that we have an x in all three terms, so we can write this as x times 2x squared minus 13x plus 18. Okay, and then we'll have to factor that quadratic expression inside the parentheses. And so how do we factor this? Well, it might be a little trickier to factor this, but we'll need a 2x and an x, so that 2x times x gives you 2x squared. And we're going to look at some ways to multiply things to get 18. You could do 1 times 18, or 2 times 9, or 3 times 6. You kind of have to decide which goes where. And it's a little bit of a trial and error. But what I think works is 2x minus 9 and x minus 4. Because if we multiply this out, 2x times x is 2x squared. We have a minus 9x from the inside two terms and a minus 8x from the outside two terms. Oh, I'm sorry, that's supposed to be a 2 there. Okay, so we get a minus 9x from the inside two terms and a minus 4x from the outside two terms. That gives us minus 13x, and minus 2 times minus 9 gives us plus 18. Okay, so what are the numbers that are excluded? Well, x equals 0 is excluded because of this x here. Okay, x equals 2 is excluded because of this one. And what number is excluded here? Well, it should be 4.5 or 9 halves. Now, if you weren't sure of that, what you could do is set 2x minus 9 equal to 0 and solve that for x, right? We have 2x equals 9. Divide both sides by 2, you get x equals 9 halves. Okay, so those are the three numbers that are excluded from our domain. And so notice that if we put these on a number line, we'd have 0 here, we'd have 2 here, and we'd have 9 halves over here, which is 4.5. So those are the three numbers that are excluded. So if we're going to write it in interval notation, it'd be the interval from minus infinity to 0, union the interval from 0 to 2, union the interval from 2 to 9 halves, union the interval from 9 halves to infinity. Okay, now what does the graph of this function look like? Oh, before we get to the graph, I want to point out one more thing. Notice we have an x minus 2 factor on the top and we have an x minus 2 factor on the bottom. Wouldn't those sort of cancel out? And then maybe 2 really will be a part of the domain? Well, the fact that we have these factors that would kind of cancel out, that doesn't give us that 2 is in the domain, because if we plug in 2, if we want to find out what's f of 2, we would get 0 divided by 0, and that's undefined. So at x equals 2, we're going to the function's not going to be defined, so it's going to be excluded from the domain, but the graph is going to be a little more interesting at x equals 2 than at these other ones. Okay, because at x equals 0 and x equals 9 halves, we're going to have vertical asymptotes, whereas at x equals 2, our graph will have a hole in it. And here's the graph of that function. Notice that x equals 0 and x equals 9 halves, or 4.5. So that's 5 right there. This is 4.5. We have these vertical asymptotes. But at 2, we don't have a vertical asymptote. Now, it doesn't really show it on the graph here. Graphing calculators and online graphing calculators typically don't show you the hole in the graph. But actually, at x equals 2, if we were to zoom in, okay, it doesn't show it here, but there should be a hole in the graph right there at x equals 2. But you don't get a vertical asymptote. Okay, because the x minus 2 factor on here is in some sense canceled with this up here, but we still have a hole, so it's not included as part of the domain.